Okay, good afternoon, everyone. We have a very tight schedule, just some logistics before we start. It's a webinar using Zoom, so when you are not talking, please mute yourself. Everybody can hear the speakers. And we have 1.5 hours, 3 speakers, our keynote by Dr. Jacqueline Monch. And after that, we can have a little bit time for question and answers. Then we have 2 panelists, Dr. Michael Guchard and Dr. Posey. And the session will be moderated by Dr. Marshall, Dr. Duffy, and myself. And I'm Phil Young from George Mason University. So when we have the speakers talking, please mute yourself. But if you have any question, please put it in the chat window, and we will get to your question once the speaker finishes their talk. So without further ado, Dr. Andre Marshall. You're muted.
So thanks. So good afternoon, everyone. Thanks so much for the opportunity to address this group. And thank you so much, Dr. Yang, for the invitation. When I've been here at Mason for a couple of years, and I joined Mason from the National Science Foundation, where I led the IUCRC program and the I-Corps program. And so these are 2 programs that are near and dear to my heart. And I was very happy to see Dr. Yang's IUCRC and its maturity over the years, and delighted to hear about his ambitions to start a new IUCRC. I know how thoughtful you have to be in order to do this, and what a high bar it is that NSF sets to make sure that these IUCRCs are really addressing national needs. And when I heard about this webinar series as a way to explore the possibility of a new IUCRC, that's absolutely a best practice. And so I'm just delighted to be here and very pleased with the tact that Dr. Yang is taking in getting a potentially new IUCRC off the ground. Thank all of you for spending your time here, and I'm really looking forward to the speakers. While I am triple booked for this afternoon, I will have to bow out early, but we have a great lineup of speakers, and I'd like to start off by introducing Dr. Jacqueline Lemoine. I practiced. It's not perfect, but I did practice. So I'm very happy to have you here today. She is the manager of the Earth Science Technology Office in the Advanced Information Systems Technology Program. And prior to managing AIST, Jacqueline was the Assistant Chief of Technology in the Software Division at NASA Goddard. She also has had roles in the Space Technology Mission Directorate at NASA. And before that, she was a research scientist at my former home institution, University of Maryland, and a very accomplished researcher, having over 180 publications and even a patent, so translating some of those technologies. And really excited to hear what she has to present in the area of digital twins. And without further ado, I will turn the floor over to Dr. Lemoine.
Thank you very much.
By the way, Dr. Marshall is our Vice President for Research.
Oh, pardon me.
Yes, thank you very much to Phil for inviting me, and thank you to Dr. Marshall for a very nice introduction. So today I will be talking about what the AIST program is doing in the area of Earth System Digital Twin, or ESDT. So the digital twins in general have a long history in engineering, for example, for aerospace infrastructure and automotive industry too. And very more recently, they have gained interest in the health sciences, and even more recently in earth science. So why are we interested in? We can go to the next slide. Why are we interested in digital twins for earth science? So it comes from the intersection of several developments. The first one is that we are arriving at a point where we have been collecting data for the entire Earth and various types of data for now more than 50 years and continuously from various sensors and from various viewpoints, and added to the commercial remote sensing data that are going to that are now coming for use, and also the Internet of Things. We have very large amounts of diverse data that is becoming more and more difficult to access and to utilize. And at the same time, because of climate change and its impact, there is a much greater interest in many types of users to use this data. And many of these users are non-traditional users, but would like to analyze and integrate all of this data to be able to take decisions. So this is also a new requirement. And finally, because of the advances in computational visualization capabilities, but also the very big advances in artificial intelligence, and especially in machine learning, extracting information from all of this data and fusing all of this data, and being also to make the complex models run faster becomes possible. So all of this together is really bringing us to using digital twins in earth science. So I'm not going to go through all of these definitions. This slide is just to show that there are different definitions of digital twins for earth science, but more or less they all come back to the same type of ideas. And we can go directly to the next slide. So for AIST, we define the Earth System Digital Twin, or ESDT, as a dynamic and interactive information systems that has mainly three components that we will see on the next slide. But mainly what characterizes a digital twin and how it differentiates it from an Earth system model is first of all this two-way integration of this two-way integration and information access from the observation systems to the model. So this is something that has not been studied too much, but right now there is a path from the observation systems to the model, but not so much in the other direction. Also, the fact that machine learning can be used at many different levels in a digital twin, and can be used for, especially for improving the spatial resolution and also the temporal resolution of models. And so with all this, and also the very last thing about I mean the other thing about Earth digital twin is that it's the idea of being able to integrate a traditional Earth science model with human and social systems also. So we can go to the next slide. So in AIST, we really define an ESDT as made up of three main components. The first component is a digital replica, and this is often what people call a digital twin, the digital replica. So the digital replica really builds an integrated pictures of the Earth or the Earth system with the past and current states, but it's mainly the current state of the Earth or the Earth system. So this is what we call the what now. The second component is a forecasting. So based on this current state of the system, how is going how is the Earth or this Earth system going to evolve over time under nominal conditions? So this is the forecasting component or the what next. And the third component is impact assessment, is based on the current state of the Earth system and based on the different forecasting that will happen. How can we see what will be the impact of one Earth system on another, or one human system on an Earth system, or the human system or the Earth system on the human system? So this is what we call the impact assessment, and it's a possibility to build different pictures of the Earth system under different hypothetical what-if scenarios, and this is what we call the what-if. So and around it we have this information system. So there are many questions that have been asked about digital twin, and the first one is, what are the benefits of this digital twin to Earth science? And to be able to respond to that question, we have been building different use cases that I will present in a little bit. I already addressed a little bit this difference between ESM and digital twin, but this is something that we need to address more. What are the main different architecture components of a digital twin? Should we look at a global digital twin or at regional or local digital twin? So this is also something that needs to be addressed. I already talked about the role of machine learning. We can talk about the role of open science, which computational resources will be required. How will the model be interconnected? Which kind of interoperability do we need at the level of the model? But how do we? But the interoperability is at many different levels. So what is also the interoperability between digital twin? How can we federate this digital twin? If we imagine that we have many local or regional or thematic digital twin that are being built, how can we federate them to be able to get a global and more exhaustive digital twin? And finally, the sustainability, the governance are also, and the cybersecurity are also questions of interest. So if we go to the next slide. So I already talked about the local versus regional versus global digital twin, and if we look at this aspect, we can imagine a future where there will be a sort of a web of digital twin that will be coexisting in a hierarchy or in a network, and we really need, and this is probably the biggest challenge, to be able to connect and federate this different digital twin a little bit in a World Wide Web type of interoperability. So interoperability and standards and protocols need to be developed at many different levels, and syntactic, semantic, legal, and also organizational. Coming back to the three components of a digital twin, what is a digital replica? How do we build it? Which kind of data representation and data access do we put in place? Are we looking at data cubes, data lakes, on-demand data? And also, if we want to build a digital twin that goes from that can be used by from what we call from the farmer to the scientist, how do we visualize the outcomes of a digital twin? And this visualization can be done at many different levels, depending on the type of users and depending on the use of the digital twin. So in this visualization and in the digital twin itself, depending on the domain, depending on the user, there might be different user interfaces, different type of interactivity, and also what will be the refresh rate, which type of latency do we want to look at. And of course, there are all the different machine learning challenges that come up with it. So if we go to the next slide. So just it's about the same thing in a different form. So the red part represents the digital replica, the green the forecasting, and the blue the what if scenarios. So for for each of them, there are some toll technologies that will need to be developed, and they are all represented on that side. And one particular one that is very important is uncertainty quantification, which will need to be assessed at every level, at the level of the sensor data, at the level of the fusion of this data or the assimilation, but also in the machine learning. If we build surrogate models, the uncertainty of these surrogate models will need to be assessed, and even if for decision making, in the what if scenario, which kind of, if we run different simulation, what is the uncertainty of this simulation? And so at the end, if there is a decision making process, what is the uncertainty of the decision that is taken at the very end? So uncertainty is becoming very important for digital twin. And if we go to the next slide. So in AIST, we previously had two thrusts: the novel observing strategy thrust and the analytic collaborative frameworks thrust, so NOS and ACF. And they both look at two different parts of the data lifecycle. NOS looks at novel ways to acquire the data, especially based on distributed sensing, but also taking advantage of the entire portfolio of missions that exist, and potentially augmenting them or integrating them. And the second part, ACF, looks, once all of this data and various types of data have been collected, how do we analyze, integrate, and run different models and provide visualization based on all of this data and information. So really, NOS and ACF are the stepping stones towards building this Earth system digital twins, with NOS that will enable this continuous ingest of real-time or near real-time or timely data into the digital twins, and ACF that can be the basis for providing the digital twin core engine that will run behind building this digital replica. So if we go to the next slide. So coming back to machine learning is extremely important for digital twin. It is important at many different levels, and I am not going to read all of that, but I already mentioned a few of them. Probably one of the most important one is surrogate modeling, but also another part that I didn't talk about is being able to speed up the what if simulation, and also enabling causal analysis and impact assessment. So machine learning in this process of trying to determine how one system can impact another one will become very important, and it's probably a topic which has not been studied too much until now. And machine learning could also be very important in the visualization process, to be able to speed up this visualization and also to react differently depending on the types of users that are using these interfaces. If we go to the next slide. So in October, in 2021, we ran an AIST solicitation with ESDT as one of the new thrusts. So these are all the different technologies that were requested in this solicitation, and as a result of the solicitation, we selected four projects related to ESDT. And they cover four different areas. The first one is more general about which kind of infrastructure do we need for ESDT, what comes in this, what are the components of this infrastructure. The second area, of course, very important, the surrogate modeling for ESDT. The third one is what I talked about with the SEF that can become a basis for building this digital replica. And finally, we have a few projects who propose the ESDT prototypes. So in the next few slides, if we go to the next slide, I am going to show and this is just I am not going to go through all of these projects. This is just to show the different projects in the different domains. And you can look at all of them online on the AIST website. So in the interest of time, so there we have the projects that are more related to SEF for ESDT. If we go to the next slide, we have a few projects looking at infrastructure. So looking at data assimilation, visualization, uncertainty quantification, and the last one on reproducible containers. If we go to the next slide, we have projects related to the surrogate modeling for different applications. The first one for atmospheric RC interactions, the second one for atmospheric composition, and the third one looking also at uncertainty quantification and kernel flows. If we go to the next slide, we have finally the prototype. So we have three prototypes. One that looks at agriculture application. The second one that is now part of the Fire Tech program, looking at wildfires. And finally, the third one for hydrology, and especially looking at developing very advanced techniques for surrogate modeling. So if we go to the next one, we have also a project that started before the solicitation, and which is a collaboration with the CNES. It is based on a flood prediction and analysis system that was built previously, that was called FloodDAM. And then FloodDAM ML was developing, if we can, yeah. FloodDAM ML was developing machine learning techniques for this flood analysis, and based on this flood detection and monitoring system, we are now building a digital twin that is looking at flood detection and monitoring at the impact of different systems on the floods, but also at the impact of the flood on the population, and particularly looking at city infrastructure and how floods can impact city infrastructure. So for this particular digital twin, there are many different models that are going to be interconnected, different types of data, and it is also a prototype project to look at federating two digital twin systems. So since there will be one system built at CNES and one at NASA, we will then look at federating these two systems to produce the final digital twin. So if we go to the next slide. So as I said, it is very important to justify, to show that we are not just playing in a sandbox developing these digital twins, but that these digital twins can be extremely useful for the future of science. We are developing a certain number of science use cases. These are the 5 use cases that were developed during the workshop last October. So there is one on wildfire, one looking at ocean carbon, one for water cycle, and one a little bit different, looking at carbon corridors in Central Africa. And there it really integrates issues of carbon as well as biodiversity, but also economic and policy decisions that and of course everything related to climate change. So it's probably a pretty widely involved digital twin. And finally, we have a last one on atmospheric boundary layer. After the workshop, we also started developing an additional use case for a coastal zone digital twin. And this is done in collaboration with NOAA and CNES. And so this is what we call the grand vision for this use case. Of course, we are not going to implement it just in one time. We are probably going progressively, and we are going to see if we need to develop smaller digital twins that federate to provide this coastal zone digital twin. We are still in the process of defining the architecture. If we go to the next slide. So what's next for ESDT? So of course, we would like to develop a few other use cases, especially as they relate to the new strategies that has been defined by the Earth Science Division at NASA, which is called the Earth Science to Action strategy. So they have defined 13 different areas of interest for this strategy, and we are going to try to relate these use cases to this strategy. In terms of technologies for AIST, there are some overall capabilities that will be needed in this exchange of information between observing system and models, but also in the machine learning domain and in uncertainty quantification, and also in visualization and interactive capabilities. From an end-to-end Earth system digital twin, we are looking at defining some general digital twin architecture, but trying to see how there can be an overarching type of architecture, but maybe different ways to implement it. Of course, interoperability standards federation is very important, and a few other things that I already talked about. So I will probably go to the next slide. So yes, so in summary, we spend a lot of time trying to define very accurately what we call digital twin, because we thought it was very important. So the solicitation selected these different projects, which are now at the end of their first year, and at the end of the second year, some of them will probably coordinate to develop prototypes, other prototypes. We have started collaboration with other agencies like NOAA, USGS in US, and CNES and ESA outside of US. We have ongoing collaboration with the CNES, and we are starting the same type of collaboration with Destination Earth and ESA, with which we have regular meetings, and we are organizing joint events at different conferences like EGU, AGU, and we will have a town hall at IGAS on this topic. If we go to the next slide. So there is a report that is now in a complete draft form that summarizes the workshop of last October. We hope that it will be online at the end of June, maybe early July, but it's about complete right now. So it will be publicly available on the AIST website. And if we go to the next slide, which I think is my last slide, I just wanted to show this link where you can find information about all the different ESTO projects in general. And if you choose information system on that page, you can find all the AIST projects, current and past. So it gives you usually the abstract, a quad chart showing the general objectives and the technical approach, and sometimes there are some reports available too. And I think that's it.
Well, thank you, Dr. Munch, for the great presentation. This really shows us the vision and also what is the digital twins. Now let's we do have some time. So for our audience, if you have any question, you can unmute yourself and ask your question, or you can put your question in the chat window. So Dr. Namushi, I do have a question here. You mentioned about how the open science may contribute into digital twins. So what's your vision about how the open science and digital twins will interact with each other?
Yes, so I imagine that we have not yet defined what is a digital replica, but a digital replica will integrate not only I mean will integrate data and information. So it might integrate analysis ready data. It might integrate outcome from models, and so the open science will be very important to be able to access not only the data but also the models that created the data, and being able to run models or being able to recreate outcome of models or workflows. So open science plays a large role in this access to different types of data and information that will be useful for building these digital replicas.
Yeah, there's a lot of question we have is how to define the success of a digital twin, or what are the different levels or phases of a digital twin project? You mentioned a lot of parts about, for example, uncertainty quantification or be able to aid the decision making. So do we have some kind of leveled or phased definition of the success of a digital twin project, or what's your vision of the success of a digital twin project?
Yes, there are some levels of I think levels of digital twin that have been defined by the consortium. I don't remember the exact name, but consortium for digital twin. I mean, these levels have been defined mainly for engineering digital twins. But this is something that we are looking at, is how maybe we can redefine or tweak a little bit this definition of levels of digital twin for Earth science. So we would have 3 or 4 levels of digital twins that would represent different levels of implementation. So this is one part, but the other part is how do we in our brainstorming session a few days ago, we were talking about maybe a Turing test for digital twins. But how do we validate and assess the accuracy of the results that come out of a digital twins? This is something. This is also something that needs to be defined. And right now there is nothing. I mean, it is something that needs to be defined more carefully.
Yeah, so there are 2 questions in the chat window. Can you see them? So the first one is, what are some of the ways, in fact, 3 questions now. The first one is, what are some of the ways you envision the physical environment can be updated in near real time?
Well, it really depends on the domain. I would imagine that for if it is the digital twin if the digital twin is used for wildfires, it will need to be updated very quickly. So this is where I think that the NOS focus area is very important, because in the NOS thrust we have been looking at models running and automatically requesting new data, and we have been running an experiment where we had a hydrology model determining areas where there might be potential floods in the next few days, and we were able to task automatically the Capella system and the Capella space sensor to acquire SAR data from this particular area, so we could predict more accurately the flood. So we can imagine that for a flood or for a wildfire, we can do this kind of thing and ingest this new data in real or near real time with a digital twin. Of course, if we are looking at a digital twin of glacier melting, this is probably something that doesn't happen with the same time frame. So I think that this kind of updating, it's why I don't say always near real time or real time. I usually use the word timely because it's a time dependent on the type of application that we are looking at.
Thank you. That was from Dr. Mando. The next question is from Anusa at GMU. Do you think including the Amazon rainforest as one of the use case for the carbon budget would be a vital role in the carbon budget?
Yeah, in fact, probably the use case that we defined for Central Africa could probably be applied for the Amazon rainforest. So because mainly this idea is to see what are the impact on the ecosystem when some of the forest is being cut for different purposes and with various different ways. So it's so being able to build some kind of a digital twin that would be able to be adapted to the Amazon rainforest would be probably something that would be very interesting also.
Thank you. The next one comes from Joshua from OGC and Harvard. He's asking how, if at all, do the Gemini principles factor into the AST work on digital twins?
Okay, so I have to ask. I am going to show to show ignorance there, but I don't know what are the Gemini principles.
Okay, there's a link just posted.
Yeah, I can clarify. This was work done by a 5-year project at Oxford, really on the ethics and trustworthiness, integrity of digital twins, particularly national scale digital twins. But it really has to do with, what is ethical behavior and what is the development of trust in terms of what a digital twin might be telling you about the physical world.
Yes, so this is where uncertainty can play a big role, but also I think that also it's the same principle than the trust in AI, and in fact it relies a lot of trust in AI also. So I think the same type of principle can be applied, but I agree that this is something that we will have to study also, but I think that in one sense, in a digital twin, you can also the beauty of a digital twin is that you might be able to use many different models. And so being able to look at an ensemble of models instead of one model also can help raise a little bit the trust that we have in this type of system. But I agree that it doesn't remove all the different issues.
Well, thank you, Dr. Nemours. That's really great. A lot of insights, very intriguing to the community. Let's move to the next speaker. Dr. Dan Duffy will introduce, and Dr. Duffy is the chief of the NASA Goddard System, which manages one of the 2 NASA high-end computing facilities. Dr. Duffy.
Yeah, thanks, Phil. So I'm not going to come on screen because hopefully you're already seeing Stan, who's the most important person here talking next after Jacqueline, and then on to our next wonderful speaker here in just a second. So Stan is the program manager for Earth Science at NVIDIA. If anybody knows Stan, he's like the ideal person when it comes to the mixture of technology and science. It's really fun to talk to him. He's had 20 years experience in the HPC industry. He manages a worldwide strategy of HPC applications and has a really, I think, I'm extrapolating, Stan. I think you've got your heart in earth science and numerical weather predictions. So he's going to talk about what they're doing with respect to Earth 2 and NVIDIA. And he's worked at he's been in NVIDIA for a long time, but he's worked at Oak Ridge and he's worked at other companies and he's got great experience. So Stan, over to you. Looking forward to hearing everything you're going to say. You can see your slides. Do a sound check, Stan. Let's come off mute.
Yeah, I'm muted. Thank you. Thanks for the introduction, Dan. And one quick question, please, from Dr. Yang. I'm Mr. Posey, not Dr. Posey. I wanted to correct that out of my deep respect for those who aren't PhDs. My background's in mechanical engineering. So,
sorry about that.
Well, you know, you went to University of Tennessee. We won't hold that against you.
Yeah.
Go Balls. Okay. So I'll start with just a brief introduction. I'm going to speak for 10 minutes to give you a brief introduction of what we're doing with Earth-2, but talk first about the vision. And it's really to imagine if you could select a region of the planet, ask questions regionally, locally about the climate change impacts, and then receive that information in a way that's visual, statistical, and interactive. And that's what we hope to achieve. There's others looking at the problem. Previous speaker, Dr. Limon, talked about the Destination Earth project. That provided early inspiration to Earth-2 that I'm going to describe, but we're also involved in Destination Earth. We're contributing to areas like model development on GPUs, and then we have 2 of the 3 Euro HPC systems are based on NVIDIA GPUs that will be used for running these climate models. But Earth-2 will provide digital twins of the Earth in unique ways. I talked about Destination Earth. There's a really large emphasis on numerical models there, whereas for Earth-2, we're really concentrating on the use of these large AI surrogate models and at the highest resolution possible. And I'm going to show you an example later, but we're really emphasizing the AI aspects here. Of course, the numerical models are critical to that. They provide the training data and the ground truth, and I'll get to some of those details as well. But we've got a large investment in scientific research on deep learning and physics ML, and this is not strictly computer scientists. This includes climate scientists that we brought into the organization to collaborate together. And the other emphasis here is the interactivity. And that's really important, and that can't be possible without an AI surrogate. And we have a development environment we call Omniverse, I'll describe later, but that's going to enable this activity working with these AI surrogates. And then, of course, to make proper predictions and calibrate those, we need continuous learning from Earth observation data. And I'm going to describe a little bit about that as well. So getting back to how this would operate, what's important here, really the physics-based predictions are important to provide us with the data we require to train these AI surrogates. And then we'll have those in the Omniverse as an interactive digital twin that allows you to ask the questions about regional impacts and so on that I talked about in the earlier beginning on the vision. But I want to emphasize again, these physical simulations are really important. That's providing the accuracy that we need to get AI surrogate models that will deliver the kinds of physical representation that are required. These are a number of Earth system models we're working with. I showed a list earlier, but looking at other areas where we can apply digital twins on regional problems such as flood flyers, etc., and hydrology areas. And I'll talk a little about these as we go forward. Again, the Earth observations are going to be critical for us to calibrate these simulations of the future. And organizations like NOAA, where we have a project currently, along with Lockheed, on the NOAA Earth Observation Digital Twin, that was awarded last year in 22. That's in progress, and we're also talking regularly to NASA to understand how we can benefit from their Earth observation programs in the Earth-2. Now, again, I mentioned the motivation on having this interactivity, and that's really going to be important as we start to couple these models, starting at the climate level, getting to regional weather twins. And here's a use case I'm showing for a power plant where we're looking at the electric grid model. It's really important that we have an environment with these fast and accurate AI surrogates that we can then couple in these interactive ways through this Omniverse environment that I'll describe later. So having this ability to connect these models and have them interact with each other is something that's NVIDIA is developing in this program to make sure there's a uniformity in the workflow between the various digital twins. And an example of a weather twin that I showed or referenced earlier, here you see ForecastNet, which is a system we've developed at NVIDIA based on a Fourier neural network. And that's where this Fourier forecasting network name comes from. It's a collaboration between NVIDIA and primarily the NERSC DOE National Lab. So again, a purely data-driven ML surrogate for global medium range prediction. We will extend this to climate range, and we're starting to do some of that work, and I'll show you a preview later. It's trained on the ERA5 reanalysis data from ECMWF, which offers about 35 years of reanalysis at, that should say 25 kilometers. I'm sorry, it's not 30, it's 25. Not sure why that's in there. But again, it's an adaptive Fourier neural operator architecture, and we trained on 20 input variables that you see in the right corner here. And to date, rather, when this slide was made, it was the highest resolution data model ever trained. There's been a lot of work since we published this. I'm going to show you here in a moment. But you can see the kind of advantages here. The speed up versus conventional NWP would be in the orders magnitude of 4 to 5. Again, comparing with something like an IFS, where which ERA5 is based upon. But the power saving here is also equally important, getting an order of 4 magnitude with running the inference mode. It has exceptional weather skill. I'm going to talk about that here and show you a couple of examples. So I mentioned the resolution. If you go back to 2018, when ECMWF published the first paper that's known about using a fully data-driven model, okay, that's where the entire model is now in an AI emulation. In 2018, that was published. Progressively, there's been more resolution in the models that you see that are referenced here. And then we published in early 2022 and have currently the largest resolution that's available at that time. Like I said, there's been some other developments I'm going to show you here in a moment. But that was really important to us to get to the level of skill that I'm going to show you against the ground truth of ERA5. Now today, though, you can go and find the literature, and since I'm staying close to this, you won't have to go too far. I've listed it all here. There's 7 models. There's actually 8 models. There's one that I need to add to this list. But it's interesting that ERA5 has enabled all of these data-driven models in their current development. And 4 come from big tech. That's something people are really starting to keep an eye on. And then 3 from academia. And notice there's not really any agencies involved here. That is starting to change, and there's some collaboration ongoing in organizations that I can talk about later if you like, but they're starting to recognize this work. It wasn't just NVIDIA who could show it was done. You've got Google, Microsoft, etc. And now there's a moment where it's starting to turn and agencies are beginning to investigate these. Now, I won't go into a lot of detail, but ForecastNet has shown good skill against the ERA5. Here, for example, is the ForecastNet against the ERA5. These are visual representations. Later, I'll show you some skill scores. But this would be some extreme events like surface winds, tropical cyclones, atmospheric rivers, etc. And here's a really nice visual you could see, I hope, on some of the comparisons for precipitation. And that's not something that's typically easy to predict in these kinds of models, but we did this work looking at atmospheric rivers in the Pacific, and you can see that we visually match the results of the ERA5 really well with the ground truth. Now, the most recent developments have been around this new architecture. I'm just going to mention it because it's very new work. There's a paper that was published at the ICLR, I believe it was. You can see the reference to the paper below. But we modified our architecture to a spherical FNO. And we did that to give this an underlying grid that would allow us to correct the pole problems that are typical of numerical models. And here you can see that before we had the AFNO, the adaptive FNO I mentioned, which was just on a lat long grid, you can see that we didn't do as well in the IFS as we got out to a longer number of days. But now we're at a point where these are ACC scores, sorry. We're starting to exceed, in some cases, what's possible with the IFS, which is, again, what the Aero 5 is based on, getting out to much longer timescales. And we've even shown that this has been stable out to S2S scales. And we're now starting to look at the accuracy of those, and we'll get back to you on the results there, but it looks very promising, this new development. And then just a final comment about some research, and there's lots of other research projects we're going on, but I want to mention that we're starting to look at regional scale, because that's really where climate action happens and where people care about it most. Here you see the 25-kilometer forecast. Now this would be a region over Taiwan. Taiwan itself, I don't know the actual dimensions, but 25 kilometers would not be reasonable to have resolution for that. And we've been applying generative AI to downscale, in this case, to 8 kilometers and then further to 2 kilometers. We're working with them to look at some other regional weathering modeling with the WRF model to help them implement digital twins in their operational weather prediction. And I'll just close with a quick comment on what I see as the components that are required to develop a digital twin and the kinds of components that we applied in this Earth 2 project. Certainly you need, again, the high resolution numerical models. I mentioned IFS, ICON from Germany, MPI-M is one that we're working closely with, but we'll be looking at others, including the GEOS from NASA. MPAS has been a consideration from NCAR, and then the UFS from NOAA. A quantity of observation data, that's starting to happen with this project we have ongoing in collaboration with Lockheed for the NOAA EODT project. That's just getting started. I think first deliverables for that will be later this year. You'll start to hear more about it. And then, of course, advances in deep learning and the physics-informed machine learning. I haven't talked about the physics-informed directions for our work, but that's certainly coming. Again, everything at the moment is data-driven, but there will be opportunities to improve the physical realism through a physics-informed approach. The NVIDIA Omniverse is critical to this. In our case, this is what provides us the connections between the different models of disparate data, and then allows that interactivity through visualization, where most of the images that you saw earlier were generated from that. Then, of course, GPU-based supercomputing, especially for the HPC models, but also for the AI training, which can be at very large scale. And then collaboration with the scientific community, which we have in place with the R2 program as well. So that concludes my discussion for the day, and I'll be happy to take questions, or if we're having panel discussion, I can take them there. Thank you, Dan.
Yeah, thanks, Dan. So Phil, what do you think? We have time for a couple questions?
Yeah, we could have time for 1 or 2 questions.
Okay, I'm looking at the chat. Feel free to drop it in the chat or just jump in, unmute yourself.
Yeah, in fact, I do have a question for Stan. You mentioned about the climate models. Some of them, in fact, most of them probably are based on numerical methods. You also mentioned that they are AI-based, for example, the generative AI to downscale the data sets. So what's your experience on using both type of models to do climate or other Earth science research, and how the GPU is supporting that interaction between numerical methods versus the AI?
Okay, there was a lot in that question, Phil, but let me start at the numerical model level. If you notice, I've really talked mostly about atmospheric models, and that's because getting to these really high resolutions, we haven't yet gotten to the fully coupled models in the way that we need. We've done some work. If you noticed, if you know the Diamond project, which was development by many in the community, but led by MPI-M and University of Tokyo, they have now in Diamond 2 a coupled approach with atmosphere and ocean. And we're just starting to train on that and see what's possible there. In fact, we've got an ICON atmosphere to ocean coupled model that we're training on, and we'll be able to show you results on that soon. So my answer on the training side, or sorry, on the AI surrogate side, is we haven't had enough experience yet. We're just getting to the experience of the training because we now have those kinds of numerical models available. But we're still far away from a fully coupled global model, right? We've got other components that we need to include besides just atmosphere and ocean. I guess my summary there is that we're just not at that point yet, and we're really focused on atmosphere at the moment. But there was something else in there that I missed. Sorry.
Oh, seeing how the GPU computing is utilized to support the modeling.
Well, yes, absolutely. We intend to have the models running on GPUs in order to get the fast turnarounds required. Well, just to make the models manageable at that resolution. If you notice, programs like NextGEMS, which has been developed in Europe out of MPIM, they have a target for going to cloud resolving ESMs that will have 1 kilometer global for the atmosphere. I mean, you can't, I don't think you could manage that kind of scale without a GPU implementations. So we're working closely with that to make sure that's there. But we're seeing that for some of the other components, even ocean and sea ice, land model, et cetera, you could probably run those on the CPU behind the atmosphere running on the GPU because it takes so much of the computational time compared to the other component models. So we've been investigating those. You know, it's a matter of the coupler being able to manage that sort of workflow, but we've made pretty good progress looking at that with the atmosphere ocean I talked about. That's the approach we're taking there for that coupling.
Okay, thank you, Stan. And thank you, Dr. Duffy. Our next panel speaker, Dr. Michael Guchard. Dr. Guchard is a distinguished professor emeritus at UCSB. Before he retired, he held the Jack and Nora Benjamin Chair of Geography over there and directing the UCSB's Center for Spatial Studies. He also directs the National Center for Geographic Information Analysis, which sets the foundation for GIS science in the past about 3 decades now. And he was elected as the member of the National Academy of Sciences in 2002, and was elected as a former member of the Royal Society and corresponding fellow of the British Academy in 2010. And in 2007, he received the Prix Valentinade. That's the Nobel Prize for Geography. So even after he retired, he's still providing the leadership and pointing the future directions for geography and geospatial research. So Dr. Guchard, please.
Thank you, Phil. Thank you for that introduction, and thank you for the invitation to do this. We've heard 2 very exciting presentations and seen lots and lots of images. So I think at this point, it might be best to just sit back and take a broader perspective and ask some questions about the broader significance of this whole development of digital twins. So I want to say a little bit about an older concept, which is now a quarter of a century old, which is digital Earth. And I also want to raise some of the ethical issues, which certainly to me arise in any discussion of digital twins. So just to review the key concepts, I think by now are pretty clear. There is a system, and in much of the early work on digital twins, the system was something manufactured like an airplane. But today, the main emphasis is on Earth as a system. But there are also, of course, digital twins of cities and digital twins of human beings. And there is a digital replica of the system, the data representing the form of the system, how it looks, and also digital models of the system's processes, in other words, how it works. And we've heard several references to doing this in real time. the need to constantly update as the world changes and feed that back into the model. Underlying all of this, I think, is a very important concept, which is perfection. Because if I take one of the many definitions of digital twins that have been published, this one going back to 2002, so the implication is that it probably derives from manufacturing applications of digital twins. The key element there, of course, is at optimum, any information that could be obtained from the physical object or system could be obtained from its digital twin. And that's in essence a Turing test of a digital twin. It says, can I distinguish between what the digital twin is telling me and what I know to be the truth about reality? And that's, I think, a very significant issue. We've heard about it from several perspectives. One is uncertainty, and that raises all sorts of questions about how you measure uncertainty and how you propagate it through these systems. Underlying that is something that I, as a geographer, am very well aware of, but this generalizes very well to any data of any kind, and that is the map is not the territory. In other words, the digital representation is not what it is. It's not a perfect representation of what it's trying to represent. We often attribute this to Alfred Korzybski in 1933. And it's something that I think underlies all of what we're thinking about and doing. So to the ethical issues, because if we're building these digital twins that we know to be imperfect, what are the ethical issues that arise? And one, I think, might be, is there a threshold level of perfection that allows someone to claim a digital twin? In other words, the claim of a digital twin is a fairly strong claim. Does it require a certain level of perfection in the digital twin itself? And then, if all digital twins must be imperfect, what level of perfection is needed for specific use? In other words, fitness for use. Must the definition of a digital twin be tied to specific use cases? So here is a digital twin that's good enough for this particular use case, but not good enough for other use cases. And in that sense, an ethical issue arises, which is the question of how to avoid repurposing, how to avoid the possibility that something designed and good enough for one application will be either accidentally or deliberately or in a misunderstanding applied to something for which it's not fit. And then how to measure imperfection. And it's very easy, I think, to refer to uncertainty and say that we need to measure it. But we have a serious question here, which is typically the absence of an authoritative standard. We don't know what the truth is, and therefore, how can we measure uncertainty? And of course, there are ways of dealing with that, but it becomes a particular critical issue. One question that's bothered me a lot is the why now question, because we've had perhaps half a century of efforts to simulate the Earth system, both environmental and social dimensions of the Earth system. And yet it's only recently that we've started referring to this as digital twin. Has some kind of threshold been reached that would explain the current interest in the Earth sciences? And certainly computing, data, models are increasingly abundant, but that process has been underway for many years and is likely to continue and accelerate, but it can never reach perfection. So why now? What is it about the current situation that has prompted us to use the term digital twin to refer to something that in its basic structure, we've been doing for a long time? If I go back to 1998 and a speech that was written for Al Gore when he was vice president, and he believes we need a digital Earth, a multi-resolution, three-dimensional representation of the planet. Now, in this, and it's been widely disseminated and it's easy to find on the web, in this, there is no reference to processes, stimulation, and what if. So some of the things we're expecting to extract from digital twins were not present in the original vision for digital Earth. However, they've become very definitely part of that vision since. Here's a manual that I was part of the editorial team for. It's a 2020 survey of all of the issues that have been discussed since the Gore speech. Totally open access and 850 pages. There's a lot of material there, particularly on ethical issues. I wanted, though, to introduce a point which to me has been very much the way my thinking has developed on this question of digital twins. Here's Philadelphia. And this is part of the publicity that Esri distributes for its digital twin efforts. And the point here is that we have reached the point, the spatial resolution of the buildings, the spatial resolution of the data are good enough that this image, in essence, passes a Turing test. I cannot tell whether this was a real photograph or whether it was a simulation. In fact, of course, it's a simulation, and that little object in the middle with its shadows has been added to the simulation. So this leads me to propose two very distinct perspectives. Number one, which is common, I think, mostly in urban planning, is a photorealistic 3D visualization. It's typical then for these to be called digital twins. There's typically no modeling of dynamic processes, including vehicles and pedestrians. Predictions, therefore, are probably not very likely. Is the term twin justified given the inevitable presence of uncertainty? And here's, I think, the key question. Does the use of the term digital twin lead to misunderstanding about the accuracy of predictions? This is a very limited perspective then. This is visualization, and it's driven by the existence of very fine resolution data. The very different perspective, and the one that I find most compelling when it comes to scientific applications, is this one, where a digital twin is a project to capture, preserve, and provide access to the data collected by scientists investigating questions about an area and the provenance of those data, the models they have used, the conclusions they've reached. This then is something that might be described as a repository digital twin or a digital repository. Here's an example. This is the Jack and Laura Dangerman Preserve west of Santa Barbara. It's 25,000 acres. It receives every year 50 to 100 scientists conducting various projects ranging from anthropology to hydrology to ecology. And the desire on the part of the organizers of the preserve is to keep all of the data, all of the results, all of the models local so they can be used to leverage further research. So here's a description of the objectives here from Dawn Wright, who's the Esri chief scientist. Our vision is to create a digital twin, a working model, in order that it can accelerate processes of understanding by various future projects. This then is, I'd suggest, something rather different. It's a very different perspective, not in itself a source of predictions. We're not trying to make a complete model, a perfect model. No obvious relevance for the Turing test then. And the belief that new discoveries will come from the research that is leveraged by the twin and not from the twin itself. And I think that's a very useful perspective as we go forward in developing digital twins, to think about, as I've suggested, two very different forms. One with an emphasis on visualization, and I've emphasized there its relevance to urban planning, and this, which is much more, I think, relevant to the earth sciences, and also, though, not excluding the social sciences, because there are quite serious archaeological interests in the Dangerman Preserve. So it's easy to make a list of the missing pieces in terms of research, and Jacqueline has already done this to some extent. In order to build such a repository digital twin, we need to solve problems of data fusion and integration, interoperability, search for data and process models over the repository, integration of digital twins across disciplines, across geographic space. All of these then have been discussed in the previous two talks. And some implications for education. What are the basic principles here in building a digital twin? What does the next generation of scientists need to know about digital twins? And could there in fact be a common set of software that's used in that training process? So all of these very open and I think very challenging, very interesting research topics. So thank you very much for your attention, and I'm looking forward to some further discussion.
Do you have a question?
Yeah, well, I'd like to sort of propose a bit of a framing that maybe the panel can address, which is, I think it's clear that digital twin is a useful ideal towards which coupled models and data sets might aim. But I wonder if it results in too great of a temptation to think that it's an attainable ideal. And so it represents something of a danger in terms of, efficacy and trust in those models and data by presenting something of an illusion.
Well, I have to say, I share that concern. I think there are various things we can do. One is through the user experience of digital twins to make sure that what is presented to the user is honest, trustworthy. Another is to greatly extend our understanding of uncertainty. And remember, this is uncertainty largely in spatial data, which is never a trivial problem, and is challenged, as I suggested, by the fact that we generally lack the authoritative data to which we can compare. So a couple of ways that we can go about this. I think, quite honestly, the user experience option is the more challenging and much more worth exploring, because it would make the whole question of uncertainty and perfection live in the mind of the user.
Do we have any response to that question or suggestion from Stan and Dr. Nemours?
Well, I'd like to comment, please, on the direction that we're going with the models. As I mentioned, 1 kilometer global is a target for these atmosphere models. You just can't run many of those in a lifetime. Not only are the runtimes impractical, but just the impact on the environment from that run is unreasonable. So that's where we think the AI is going to have to play a role in order to have these surrogate models. Because ultimately we'd like to go to ensemble prediction. How could we possibly do that with these high resolution? That's my comment, please.
Yeah.
I don't think we have a choice. I guess that's my summary.
Thank you. We have Dr. Nemours. Do you want to respond to that comment question?
No, I didn't have any specific response. Go ahead.
Okay. Yeah, we have a question from Dr. Wendy Guan from Howard.
Thank you. The presentations and the discussion is fascinating. Just to follow up on the conversation between Josh and Mike, actually, in terms of how do you handle the misconception that the name digital twin might generate in the naive community. From one part, I certainly see the point that when visually you can almost fool the human eye that the representation, the digital representation, looks exactly like what their camera could produce from a snapshot of the reality. But if you ask in-depth questions to the digital twin, the models may or may not be fit to answer your specific question, and really depends on the purpose and everything else. But exactly because the visual promising, right? I think it's more important almost to engage in this digital twin concept because the community, the population is going there anyway. And if we could inject the uncertainty, the suitability, the the purpose behind, and then also understand that every digital twin has its specific purpose, but there are many digital twins. I think we in a different occasion had some discussion on that too. Need to work together and complement each other. So perhaps the digital twin research could have a new focus in terms of how to communicate and how to guide the population, the general public, to use these different twins for different purposes properly, and also guide the scientists who are building these specific purpose digital twins to complement each other and interoperate to some degree. Would that be in itself a research direction? Sorry about the long winding question.
Yes, absolutely it would. I think that in suggesting that the secret here might lie in the user interface, the user experience, I think there's abundant room for human subjects experiments to find the best ways of doing that. How do you, for example, arrange to pop up messages when people appear to be heading in certain directions that are not as trustworthy? How do you do that? How do you avoid people always turning off those pop-ups? There are all sorts of questions there. But bringing the humans into the loop, I think, is really essential.
Do we have some response from Stan and Jacqueline on Wendy's question? Okay, there's a question in the chat window. I think that's probably for Mike, if you can see the chat window. In terms of building a digital twin city, it seems to be an effort of model results to be integrated and displayed in a 3D environment that could have been displayed in multiple 2D maps. To ask about your first perspective, isn't this then an exercise in upgraded visualization of our results with interactivity to the model added on? So what new aspects does it bring when compared to developing this as a CyberJS framework?
Interesting. I think that there are a lot of directions that we can head in attempting to build a digital twin city. One is very close to real-time need for traffic simulation, particularly simulation of traffic during emergencies or during events. Then there are much longer-term issues such as dealing with urban sprawl, which might be done as a process of simulation modeling. To try to simulate try to implement some simple rules about how cities evolve. And that's out there in the literature. So is the traffic modeling option. So is a lot of recent work that is tracking individuals and modeling their travel behavior based increasingly on the cell phone data. So I think there are lots and lots of ways in which that could go. I think it would be a mistake to stop at the fine resolution visualization that we are currently emphasizing in building digital cities, which then can help the planning process. And that's something that is, I think, a very challenging area. One very different from the kind of things that Stan was talking about. One very different from many of NASA's traditional concerns, but nevertheless, I think very promising and very helpful.
In fact, I wanted to add, because we are also looking at urban digital twin, but from related to climate change. and it's to assess the impacts of climate change on the urban environment. So it was especially with, for example, the hurricane, for example, Sandy, what happened to New York City with Sandy. So how can we, so the idea of a digital twin there would be to be able to look at different impact scenarios depending on weather and extreme events, for example, and the impact on the urban population, for example, or even heat islands depending on the temperature. So there are many different aspects, and this is where also we are looking at this kind of hierarchy of digital twins, because if we this kind of urban digital twin could be linked to a weather or potentially a climate digital twin. Although I don't think that we will come to a climate digital twin very quickly, but even just relating our urban digital twin to a weather to a global weather digital twin might be very helpful, and might help the decision makers take a real-time decision in case of an extreme event.
Yeah.
Yeah, for our audience, please put your question in the chat window, either for one of our panelists or for everyone, or any comments, please put in there. I saw that Stan responded to one of the questions asking how the Amazon rainforest may be considered in the carbon budget. And Stan said this is a use case that NVIDIA and collaborators are investigating. So Anusa and Jiakang, please contact Stan at the email that he provided if you want to learn more about that. And Josh, is that a comment or is that a question?
It's an invitation to comment. How about that?
Okay. So Josh mentioned here that OGC is focusing a number of its standards, outreach, and innovation activities on the digital twin concept because it represents in many ways today's preeminent challenge to and test of interoperability and effective spatial data sharing. Yeah, that's a very good comment. In fact, interoperability is a key, and it's been mentioned, I think, by all our speakers. So there's a cross-cutting question, as you may notice from our audience. Most of us are from the academia or the research division of a company or agencies. Could you, from your perspective, lay out what are the exciting research directions or new opportunities that may come up in terms of digital twins for research, either fundamental research or innovation research or application building, according to, for example, LASA standard TRL 1 to 3 or 4 to 6 or 7 to 9. So what is the top research opportunities and challenges that you think would benefit the community?
Well, I mean, I try to put them on the slide, but I think that in general, a digital twin can be considered as a system of systems that is very complex. So I think that any research in this and it's really I really like to call it an information system. So like that, it doesn't. It really builds on top of everything that has been done in the last 40 years or so in earth science and earth science models. It doesn't try to recreate anything that has been done, but the main difficulties is bringing everything together, and I think that this is where the biggest complexity lies, I think.
Thank you. Mike, I think you enumerated a list of 10 probably challenges. What's your top 3?
Well, I have to say uncertainty, because I think that's something that I've been working on for a long time, and it really is a very challenging problem. However, for all sorts of reasons, it may not be the one that is most impressive to the rest of the world. It's messy. and its conclusions are not the kinds of clear-cut conclusions that people expect. The other one that I think have much greater hope in is the user experience. Once we start building user interfaces to digital twins, and there are some examples, of course, already. Once we start that, there are, I think, a lot of very interesting questions which we can look at in terms of how people make use of these systems, what kinds of decisions they make based on them, and how we can improve the user experience. I come from the GIS perspective, which has a user experience that was laid down almost 50 years ago and has changed very little since. And I would love to see progress in that area. Also the search processes, because I think we have become really quite good at searching for data, but much less good at determining the fitness of data for use, and much less good at searching for models and results. And both of those, I think, are going to be essential in that world of digital twins.
Well, thank you, Mike. Stan, what's your top research questions?
I'm not sure the top one, but I would say one that concerns NVIDIA that we're putting a lot of efforts into is ensuring the quality of data, understanding, in some cases, there are more data than you really want to do your training, making sure you're choosing the right data for that training, and ensuring you have a ability to apply an effective ground truth calibration.
Training data sets, validation, and ground truth.
Yeah.
Yeah, thank you, Stan. There's a comment or question from Wendy among the challenges, the sustainability of the digital twins, how to keep them working when technology evolves, such as version upgrades.
Yep.
Yes, this is an important one. I mean, go ahead, Mike. If
Well, I wanted to recall that Stan, in fact, talked about the greening, the need to consider the energy consumption, the cost to the planet of running these models. And that's a dimension, I think, which needs further exploration. He suggested that it might, in some cases, determine choices. And that sort of issue has never been addressed in the philosophy of science. We really are not trained to deal with what happens when the results we would like are too expensive because of issues of sustainability or what have you.
I think that also we need to look at architectures for a digital twin that are flexible, that do not tie the system into one specific. I mean, where all the components can be interchangeable, where we can evolve at the same time. The question was when the technology evolve. I think that it's very important to be able to have systems that can evolve with the technology, that are not locked into what we can do now. But otherwise, we cannot reprocess. And NASA, we are very good at reprocessing the data relatively often, not often, but when needed. And I think that we will not be able to afford to reprocessing everything, but we will have to be able to evolve with when the technology evolves. So having architecture that are flexible enough to allow this change in technology is very important.
Well, we are at about we're 2 minutes past the 3 p.m. Mark. Thank you for our 3 distinguished speakers. Exciting, very exciting and intriguing to us. We will take that exciting moment, continue this as a monthly webinar to discuss different aspects. So we will send out emails to everyone regarding the future discussions. And thanks again to our 3 distinguished speakers. Thank you. And thank you all for coming.
Thank you. Mhm.